Hello everyone, I am Sci Geek and I am gonna be switching it up for today. Usually I do lifting streams and that's been all I've done on Twitch for the most part, or it's the majority of what I've done on Twitch. But my background is actually in applied physics and I'm gonna try a new thing a couple times a week, and that's gonna be going over the electromagnetism. I'm going to be following Introduction to Electrodynamics, the fourth edition by David Griffiths. This is an easily downloadable book. I won't tell you where, but Google is your friend. Um, and from this, I am going to go through the foundations of electrodynamics, mostly focusing on electrostatics because that is the majority of the foundation of electrodynamics. You got to learn how things stay put, how things change when everything's not moving. Then you can get into the dynamic part of moving charges and moving fields and whatnot. So let us start off with going over some of the basics. And that is going over the fundamental things that we are going to be looking at. So there are kind of four realms of physics. There, and that all depend on how fast something's moving and how big something is. So you have relatively big, slow moving objects, which is mostly governed by classical mechanics. You have relatively small, slow moving objects, which is governed by quantum mechanics. You have relatively big, fast moving objects, which is governed by special relativity. And finally, you have very small, very fast moving objects, and that's governed by quantum field theory. We are going to be just focusing on classical mechanics. Um, so these are slow moving objects that are big. Now, what is big? Big is collections of molecules and atoms. So enough such that you can approximate their energy distribution as a continuous spectrum, rather than a quantized spectrum, meaning that they come in discrete packets. Now, what is fast and what is slow? Fast is fractions of the speed of light. So if we're moving at 20% the speed of light, then we need to look at either quantum field theory or special relativity. But if we're moving a lot slower than that, we're talking less than a percent or two of the speed of light. Classical mechanics usually is a good approximation for that kind of thing. So let's get into the first stage of electrodynamics, which is uh, understanding vectors. Now, we are going to use vectors for a lot of things, and we need to understand what type of uh, things vectors can describe. So, vectors are something that have both a magnitude and a direction. So, the magnitude is known as the length of the vector, and the direction is where it is exactly pointing. So, the example here, they use the position vector um, to denote walking 4 miles north, then 3 miles east. You've gone 7 miles, but you're only 5 miles away from where you started. Um, so we're going to learn how to manipulate these quantities of vectors. So first manipulation is the negative vector. So a negative vector just reverses the arrowhead of the vector. So you have a vector A pointing in one direction, then negative A is pointing in the exact opposite direction. So when we talk about vectors, I've skipped over this. A lot of things are going to be defined as vectors. So forces are vectors, velocity, acceleration, momentum, position can be described as a vector. And things that we'll get into in this course, such as electric fields and magnetic fields, are all vector quantities. Things that are not vectors are called scalars, for the most part. There are things called tensors, but we won't get into that. So scalars have just a singular value that defines them. They don't have any direction or anything like that. They're just something like the mass of an object, how much matter is in that object. The charge, how many charges are on that object. The density, how dense the object is, and temperature, how hot or cold an object is. These all have just one quantity. They can be defined in terms of functions and whatnot, but at any specific instant in time, they will have a particular quantity. So, we will then go into 4 different vector operations. So there's one way to add vectors, and there are 3 ways to multiply vectors. Subtraction of vectors is just addition of vectors with a different name. But multiplication of vectors can be done in many different ways. So we want to understand how to both add and multiply vectors together. So addition of vectors is simply placing the tail of one vector onto the tip of the first vector. So you can see here, we start out with a vector A and a vector B, and the quantity A plus B is the resulting vector of going from tail to tip, and the quantity going from tail to tip. B plus A is the same thing. B plus A. You reach the same point, whether you go B first or A first. And that is the first statement, that vectors are associative. Addition is associative. A plus B is equal to B plus A. Like I said before, subtraction of vectors is simply adding a negative vector. So A minus B is simply A plus negative of B. So you have A, you flip B around, and you put its tail on the tip of A, and you see where its tip ends up. And that is subtraction of vectors. So that is defined here. A minus B is equal to A plus the negative of B. The next thing that we can talk about is multiplication by a scalar. So again, scalars are things that do not have any direction. They are just a singular quantity. And when you multiply a scalar by a vector, you're and this is where it gets its name, you are scaling the vector in a value. You are changing the magnitude of the vector. So the multiplication by a scalar is also distributive. You can see that scalar A plus B is times a scalar is equal to the scalar times A plus the scalar times B. And we can go over proofs of these as we define terms, and in some of the homework problems, which we can go over. So finally, we have the dot product of two vectors. So the dot product of two, sorry, not finally, we've got two more multiplications. So the third multiplication is the dot product of two vectors. Now, the dot product is seeing the projection of one vector onto another. Mathematically, it's defined like this. It is a scalar quantity. The resulting value is a scalar quantity, and you are simply taking the magnitude of A, the magnitude of B, and you're multiplying it by the cosine of the angle between them. Now, what does that look like? So let us take a look at that. So if I have some vector A, and then I have some vector B, so I want to find the dot product. So what I do is I take the magnitude of A, so the length of A, multiply it by the length of B times the cosine of the angle between them. So the cosine of the angle between them, theta, is here. So what is cosine theta? Well, cosine theta, if we drop a perpendicular, let's see if I can make this dotted. It's just straight. So I drop a perpendicular. So this is the quantity of A cos theta. So I'm multiplying it by this term. I'm multiplying this value by B. You can also flip it around. A cos theta, if I quote unquote drop a perpendicular such that this is perpendicular, that's perpendicular, then this is B cos theta. And I multiply it by A. Now, it just happens to be that B cos theta is equal to A, but that doesn't necessarily need to be the case. So, let's look at our additional properties of scalar, of dot products. So the dot product is commutative. A times B is equal to B times A. A dot B is equal to B dot A. And it is distributive. A dot B plus C is equal to A dot B plus A dot C. So the A foils across. So, like I was saying, geometrically, A dot B is the product of A times the projection of B along A, or B times the projection of A along B. If two vectors are parallel, then A dot B equals A plus B. That's because the angle between them is 0, and the cosine of 0 is 1. For any vector A squared is defined as A dot A. If vectors are perpendicular, then A dot B is equal to 0. Again, if you look at our original definition of the dot product, that is because cosine of 90 degrees, which is going to be the angle between the two vectors, is going to be 0. So A dot B is 0. Doesn't matter what A and B are, if they're perpendicular. So, like I was saying, you have A, you have B, you have the angle between them, and you drop a perpendicular, and you've got the cosine of A times B. You drop a perpendicular down this way. You've got the cosine of A of B times A. Okay. Refer to figure 1.7. Okay. Calculate the dot product of C with itself. C dot C is equal to A minus B dot A minus B. A minus B dot A minus B. Now, distributing this out because we can, you have A dot A, A dot A, A dot B, A dot negative B dot A, and B dot B. Well, A dot A and B dot B are defined as A squared and B squared. And the final, 2AB cosine theta, which is the dot product definition of the dot product. And we have two of these. So negative 2 times the definition of the dot product, AB cosine theta. Now, what happens if theta is equal to 90 degrees? Well, if theta is equal to 90 degrees, then this term drops out to 0, and we have A squared plus B squared equals C squared, which is the Pythagorean theorem. So this is a general form of the Pythagorean theorem known as the law of cosines. Pretty neat. So, moving on to our final multiplication, which is the cross product of two vectors. So the cross product is a little bit more complicated than the dot product because it is not a scalar product. You're not creating just a number at the end of it. So you have a direction, and it's defined as A times B times the sine of theta times this n hat. Now, what is n hat? Anything with a hat, any vector with a hat over it is known as a unit vector. A unit vector has a length of 1, so when you multiply unit vectors by other vectors, if you multiply unit vectors by scalars, you just get 1. You can define a unit vector in any direction you want. Up, down, left, right, forward, backwards, circular directions, doesn't matter. But it's pointing perpendicular. In this definition, A cross B is AB sine theta times n hat, where n is perpendicular to the plane created by A and B. What does that mean? So if you have any two vectors pointing in any direction, you are defining a plane. You can make a rotation such that the vectors lie on the same flat surface. So you can orient a flat surface such that, another way to explain that is you can orient a flat surface such that both vectors A and B are on it. So, once you have the plane defined, you just go perpendicular to that. And the direction is defined there, perpendicular to that plane. So if you have a plane that's tilted this way, perpendicular to the plane is out. Perpendicular to the plane can be out or in, and we have to define which way it is. We use what is known as the right-hand rule. So if you define two vectors pointing in two directions with your right hand, vector 1, vector 2, your thumb will be pointing in the direction perpendicular to 1 and 2. So you can cross those over and rotate them around, and your thumb is always going to be perpendicular to 1 and 2, to A and B. So this is known as the vector product. Dot product is also known as the scalar product because you get a scalar in the end. Cross product, you get a vector in the end. So, like the other multiplication, scalar multiplication, and the scalar product or dot product, the cross product is distributive. So A cross B plus C is equal to A cross B plus A cross C. But it is not commutative. B cross A is not equal to A cross B. It is equal to the negative of A cross B. So, what does A cross B mean? Well, A cross B is simply the times the sine of theta is simply the area of a parallelogram defined by sides A and B. Remember, sine theta times A or sine theta times B will give you the height of the parallelogram, depending on how you're looking at it. And length times height is area. So the magnitude of A cross B, so this is just the scalar value of A cross B, is equal to AB sine theta. The direction is either pointing into the page or out of the page, defined by the right-hand rule. So let's use the right-hand rule right now to see where A and B are going. So if we do A cross B, we take our finger and we say is pointing in A, and our second finger is pointing in the direction of B. And in order for that to happen, the thumb has to be going into the page. If we did B cross A, then it would be easier. We would do B, which is here, cross A, which is here. It'd be pointing out of the page. An easier way to figure this out is to curl your fingers. So point your fingers in the direction of one vector, curl them towards the other vector. Wherever your thumb is pointing is perpendicular to the plane. It is defined as n hat, the direction of n hat. So because we have that sine theta term in there, if we have two parallel vectors, sine theta is equal to 0. But it still has a direction. It is pointed perpendicular to the page, but it just has 0 magnitude. So A cross A is equal to 0. So we have two problems using the definitions of equations 1 and equation 4 in the appropriate diagram show that the dot product and the cross product are distributive when all three vectors are coplanar and in the general case. We can go through these problems later if people have questions about that. But let's move on into more vector algebra. So, how much do we have here? Triple products, position displacement, and vector transforms. Then we get into differential calculus. Okay, so let's move on to components. So components are simply the linear breakdown of a vector. So you can define, and you learn this in your linear algebra classes, but you can define any vector as a linear combination of orthogonal vectors. No, that's not true. You can define a vector by linear combinations of unit vectors. Now, those unit vectors can be pointing in a variety of different directions. But one of the main things is they need to have a positive cross product. So if we're working in two-dimensional space, then as long as your two unit vectors are not parallel to each other, as long as they're not parallel to each other, then you can have two vectors be the unit vectors, which means that you can break down any vector into components of those unit vectors. Now that's pretty confusing. So we're going to stick with the simple case of orthonormal basis, also usually seen as the Cartesian plane. So you have an x, a y, and a z axis. They are all orthogonal to each other, meaning they all make right angles to each other. And they are pointed in a unit direction. So x hat is pointing along the x-axis. Y hat points along the y-axis. And z hat points along the z-axis. So you can see that this vector A can be defined as a component along the x-axis, a component along the y-axis, and a component along the z-axis. Very very straightforward. So we broke up A into its component parts. Now, if you took Physics 1, dealing with Newtonian mechanics, you should be familiar with breaking up a vector into its component parts. You have to do this for a lot of force diagrams to determine how things are moving. So what we have here is A is equal to the components along the x-axis, the y-axis, and the z-axis. The value to determine what ax, ay, and az are, we simply dot a into the unit vector that corresponds with it. So ax is a dot x hat, ay is a dot y hat, az is a dot z hat. So to add vectors, like a plus b, what if you can't do it graphically? You're trying to add two values together. You're trying to add their tip to tail, but you don't have that information. Well, you add up their components. So a plus b is equal to the three components of a plus the three components of b. And you can only add like components together. So all of the x hat terms get added together, all the y hat terms get added together, and all the z hat terms get added together. Now, a plus b is simply the magnitude of a x plus bx. Then same for y and same for z. This also goes for scalars. So when you multiply a vector a by a scalar, you're taking that scalar and distributing across all the component vectors. So, like I said before, x hat, y hat, and z hat are mutually perpendicular. If they are dotted into themselves, they are equal to 1 because they are parallel to each other. And if they are dotted against each other, x dot y, x dot z, y dot z, they're equal to 0 because they are all perpendicular. So now we have a simple definition. What is a dot b? Well, like we said before, it's the magnitude of a times the magnitude of b times the sine of the angle between them. But what if you don't know that angle? What if you're only given components? Well, simply put, a dot b is equal to the quantities in the x direction, because a dot x hat, remember this is distributive, so you'll do a x x hat dot bx x hat, which x hat dot x hat is 1. So ax, you have ax times bx. And the other two terms, ax dot by and ax dot bz, are 0 because x hat dot z hat and x hat dot y hat are equal to 0. Then move on to the y component. So you'll have 9 components, but only 3 turn out to be non-zero. The other 6 go away because of the fact that these unit vectors are perpendicular to each other. So we have another definition for the dot product. A dot b is equal to the x components of a times the x components of b plus the x components of y times the y components of b times the z components of a times the z components of b. So again, we had the definition that A dot A is equal to A squared. So therefore, A dot A is equal to AX squared plus AY squared plus AZ squared. This is a three-dimensional generalization of the Pythagorean theorem. Now, when we look at cross products, what does that mean? Well, remember, our unit vectors are either parallel to each other or perpendicular. So if they are like, they are parallel to each other. If they are unlike, they are perpendicular. They're all mutually perpendicular to each other. And with cross products, if the numbers, how do you do two-dimensional Laplace transforms? Ferris. Two-dimensional Laplace transforms are more in Calc 3. We are doing vector dimensions, but if you want Laplace transforms, we can talk Laplace transforms. Right now, I'm just going over vector transformations, and I'm gonna call it right after that. So, how are you doing, Ferris? How's everything going? Are you in school? Let's see. Let's erase all of this. Okay. So you want two-dimensional Laplace transforms. The Laplace transform Laplace transform of f of x is equal to the integral of f of x times e to the s of, sorry. No, I'm currently in my bachelor's thesis, but sadly I didn't learn that. That's a shame. I gotta remember my Laplace transforms. Laplace transform. 0 to infinity, f of t, e to the s minus t. S minus t. T. dt. So, and we go from 0 to infinity. So that's your one-dimensional Laplace transform. If you have a two-dimensional function, Laplace of f of x and y, then the Laplace transform in the x is simply going to be this. And the Laplace transform in the y, so we go from 0 to infinity, for both x and y, transformation, f of s, and then we'll define our new variable, let's call it u, because t is taken up. E to the negative, this is our first one, st, times e to the negative u v. d T, D, V. So that's your two-dimensional Laplace transform. Very basic. What those functions are and what they mean, that's a whole nother story. But it gets complicated from there. Laplace transforms I've used them for solving differential equations, because when you take the Laplace transform of a differential equation, you get an algebraic equation. You solve the algebraic equation, transform it back, and you have a solution to your differential equation. Very handy. But that is that. So there's your two-dimensional Laplace transforms. So what are you working on for your thesis? You doing anything fun and interesting, or just kind of looking for something at the moment? Now, as I was saying, I've never encountered two-dimensional Laplace transforms. I've encountered two-dimensional Fourier transforms, and the Fourier transform is just a subset of the Laplace transform. Substitute S with I omega, and you have a Fourier transform. So two-dimensional Laplace transforms are not, I have not widely used them, but that's just me. So as I was saying before, when we have the cross product of two vectors, can't tell, automotive engineering. All right, that's pretty cool. It's good stuff. So yeah, feel free. Ask me any questions that you want. I'm going to be on for another couple minutes. If you want, I can continue, or I can just call it here. I will be streaming more often on probably Friday. Go from there. But the prof just told us that they or maybe Fourier is used for communications with moving objects. So yes. So Fourier transforms are very, very handy in any type of signal analysis, because you're able to break down a signal as a function of time into a signal as a function of frequency. You can see what frequency components are in that signal. Very useful for communications of many different types. But thank you for coming in, Ferris. I know it's been a while since I streamed, but I appreciate you. I appreciate you dropping in. I will be doing more of electromagnetism in the coming month. I will probably be streaming on Friday evening, Eastern Standard Time. So I'm going to call it for tonight. But if you want, you can check out my VODs, and I will have I'll have this VOD up for a while. Thinking about putting stuff on YouTube, but we'll see how that goes later. So all right, I'm gonna call it. Take care, Ferris. Hope you have a good night. I'll catch you later.